Okay, so let me make sure I mute this. Okay, so let me go to the PowerPoint, which deals with, oh, wait a minute. Okay, so this is what we're going to start our discussion with, Hess's law, a very important law when it comes to relating energy changes in chemical reactions for related reactions. Now, let me go to my full screen mode. Okay, so basically Hess's law of constant heat summation says that the heat of a reaction is constant regardless of the number of steps in the process as you go from reactants to products. So a very concise way of expressing Hess's law is what you see right here. The enthalpy change overall is equal to the sum of the enthalpy changes of the individual reactions. I don't know how many of you are familiar with this symbol right here. That's capital sigma, which is a Greek letter, and it's used in mathematics just to express sum. So whenever you see anything beside it after, or anything that comes after it, you should read it as the sum of whatever, right? So this means the sum of the enthalpy changes of the individual reactions, all right? It says here, when it is necessary to reverse a chemical reaction, then the sign of the delta H for that reaction will change. And we talked about that earlier, all right? And that will become important when it comes to problems involving enthalpy changes and Hess's law and so on. Also, when multiplying the equation coefficients, it would have multiplied the values of delta H for that reaction. So what this is saying is that, for example, if you were to multiply all the equations by 2, then that would result in the enthalpy change doubling. If you multiply right through by 3, that means that the enthalpy change will be tripled. If you multiply right through by 0.5, then the enthalpy change for that reaction will be halved, all right? So we're gonna see all of that in play. But before we move on to this example, let me just show you something here, just to simplify or express Hess's law in a simple way. Let me not use that. Let me use this here. Okay, let me clear this up. So basically what Hess's law is saying, right, is that if you have a reaction going from A to C, all right, and let's say that is delta H3 for that reaction. And let's say you can get to C through an intermediate B, all right? So you can go from A to B and then B to C, right? So that means, well, let's call this delta H1 for the enthalpy change for that step. And let's call this delta H2, all right? So basically what Hess's law is saying is that delta H3 for this system here will be equal to delta H1 plus delta H2. In other words, it doesn't matter how you get from A to C, be it direct or through some intermediate. The enthalpy change will be the same, all right? And this is very important because, for example, let's say you can conduct a reaction and measure the delta H3 value. And let's say you can measure the delta H2 value, but for some reason, you cannot measure this one, right? For some reason, you know, basically the experiment or the reaction is such that it is near impossible to determine delta H1 experimentally. Then if you know delta H3 and delta H2, if you know these two, then you can easily calculate delta H1 because delta H3 would be equal to, or minus delta H2 would be equal to delta H1. So that's basically what Hess's law is all about, all right? Okay, so to look at an actual reaction here. So we're looking at here the reaction of carbon and oxygen, right? Now, carbon and oxygen can form two products depending on how complete the combustion is. So you can start off with carbon and oxygen, and carbon will react with 1/2 molar equivalent of oxygen to form carbon monoxide, which is right here, all right? And then that carbon monoxide can itself react with another 1/2 molar equivalent of oxygen to form carbon dioxide, right? So the reaction can take place in 2 steps. Or you can have the reaction taking place in 1 step where you have enough oxygen to react with the carbon and you get the direct reaction for carbon to carbon dioxide when it reacts with oxygen. So therefore, what you can do in order to find delta HA, which is, by the way, very difficult to find out, because the reason why it's difficult to get delta HA is that when the carbon reacts with half a molar equivalent of oxygen, it is very difficult to prevent it from reacting with another half molar equivalent of oxygen. So let's say we are asked to determine delta HA. You know what delta HB is, which is the enthalpy change for the reaction of carbon to form carbon dioxide. And of course, delta HC would be the enthalpy change for the reaction of carbon and oxygen to form carbon dioxide. So it's very simple. Hess's law comes into play. Delta HA plus delta HB will give you delta HC, all right? So therefore, we can determine what delta HA is. All we have to do is find a difference between delta HC and delta HB. And let me see if I can do it here. Let me clean this up again. Okay, so let me see here. So basically delta HA, let me just write this first. Delta HA plus delta HB is equal to delta HC. So therefore delta HA would be equal to delta HC minus delta HB. And then we put the numbers in. So for delta HC, that is minus 393.5 minus 393.5 kilojoules minus for delta HB, that is minus 283.0 minus 283.0 kilojoules. And then we do the math. And according to my calculation, 393.5 minus 283.0 minus. Okay, so the answer I got here is minus 110.5. All right, so that's basically how, oh, by the way, the answer would be in kilojoules, of course, all right? So that's basically how you can do that. Now, there's another approach, which personally speaking, I prefer, gives the same answer. I prefer to write out the equations and in parallel form and do some elimination. I'll show you how to do it right here. So we have carbon solid plus oxygen, half oxygen. No, I'm sorry. Okay, you know what? Let me show you how to do that later on. Well, let me do that now. Actually, let me erase this here. All right, so as I was saying, carbon, pencil. So carbon solid plus O2 gas gives CO2 gas. And delta H for this would be equal to minus 393 minus 393.5 kilojoules, right? And then for carbon monoxide gas plus half O2 gas to give carbon dioxide gas, delta H for this would be equal to minus 283.0 kilojoules. Okay, I think I'm gonna need more space. So let me erase the top part here. So what I'm gonna do is, after erasing this, okay, so what I'm going to do is, well, firstly, let me just show you what we have here. So we have this reaction here. They gave you the delta H value. We have this reaction here, give you the delta H value. So what I'm going to do is, I'm going to flip this equation around, right? I'm going to flip this equation around, okay? Now, when I flip this equation, the sign here will change, right? So when I flip it, I'm going to get CO2 gas hold on, let me see here. To give C solid, I think I'm making a mistake here, plus O2.
Oh, wait, wasn't the one you were going to flip the one with carbon monoxide and the half oxygen?
Yeah, I knew I was doing something wrong. Yeah, you're right. Thank you very much for picking up on that. Yeah, so it is CO2 gas to form CO gas plus half O2. All right. And then delta H for this, therefore, would be equal to plus 283.0 kilojoules. All right. And then for the other equation, I'm going to rewrite it as it is, plus O2 to give CO2 gas. And delta H for that would still be equal to minus 393.5 kilojoules. Now, if you add these two equations together, right, the carbon dioxide will cancel out, and this half oxygen will cancel out half of the oxygen here, leaving behind half, right? So your resulting equation will be C solid plus half O2 gas to give CO gas. And we can get the delta H value resulting by adding these two right here. And you're going to get the same result. You're going to get 283.0 minus 393.5, and you're going to get the same minus 110.5 kilojoules. So this is just an alternative way of setting it up, which in my opinion is a better way. So I prefer to go this route. But of course, I won't penalize you if you do it the other way, all right? However, I will say that for more complex problems, you'll be far better served if you go about it the way I just showed you, all right? And you're gonna see that in the next example that I'm about to get to. So let me go back to the PowerPoint slide here. So here's the example I'm referring to. It says, and this is a typical question that you could get involving enthalpy changes. It says calculate the enthalpy change for reaction A, which is this reaction here, right? Given the data in the equations B, C, and D. So you're given these equations along with their corresponding enthalpy changes. And based on the information provided here, you're going to calculate the enthalpy change for this reaction, all right? So what I've done is copied and pasted that very same question here so that I can show you how to do this. So whenever you get a problem of this type, first thing you need to do is compare each equation to the equation that you're trying to find the delta H of. You're trying to find the item that is common between each of these equations and that equation. So for example, if you look at equation B, right? You see that B have graphite here, carbon on the left, right? And you have carbon on the left here, right? So what I would do to this equation here is that I would multiply right through by 2. Why? Because you have a 2 as a coefficient here for the carbon. So what I'm going to do is write down what happens when you multiply that equation by 2. You're going to get 2 carbon solid plus 2 O2 gas to give 2 CO2 gas. And then the delta H value that you'd calculate for it would be 2 times, let me just put it right here actually. So delta H here would be equal to 2 times minus 393.5 kilojoules, all right? And when you work that out, 2 times minus 393.5 I got 787 787.0 kilojoules. All right. Okay. So that's what you do to this equation. You multiply by 2 because you have a 2 here beside the carbon. Then for this equation here, when you compare this equation to the first one, you'll notice that you have C2H4 here on the left, whereas here you have C2H4 on the right. So what I would do to this equation is that I would flip it, right? To get the C2H4 on the right. And when you do that, the sign of the enthalpy changes from negative to positive. So therefore, when you flip it, you're going to get 2 CO2 gas plus 2 H2O liquid to give C2H4 gas plus 3 O2 gas. And when you express a delta H, it becomes 1410.9 kilojoules, all right? So that's basically what you do to that equation. You flip it because the C2H4 is on the left here, but it's on the right here, all right? And then you write down everything and you change the sign. Okay, for the last equation down the bottom right here, when you compare this equation to this equation, you have H2 here on the left, but now you have a 2 here. So what I would do, just like I did here, is multiply this equation by 2. So when I multiply that equation by 2, I'm going to get 2H2 gas plus O2 gas to give 2H2O liquid, and delta H here will be equal to 2 times minus 285.8 kilojoules. All right. Okay, so now that we have done that, let me move this up here. Okay. Oh, we need to multiply that. So 2 times minus 285.8. And according to my calculations, this works out to be equal to minus 571.6 kilojoules. All right. Okay, so now that we have done that, what we're going to do is add all these equations together. And just as we saw in the previous example I worked, when we add these equations together, what we try to do, of course, is to cancel out all items that are common to both sides, right? So let's do that here. And the first thing I recognize is that on both sides, I have 2 water molecules here and here. So those will cancel out. I also recognize that, and this might not be immediately obvious, you have 3 oxygens here, you have 2 here, plus 1 here, right? 3 oxygen molecules on both sides. So these 3 here will cancel out with those 3, all right? I also see that these 2 carbon dioxide molecules are here and here, so we can cancel those as well. So what are we left with? We're left with 2C solid plus 2H2 gas to give C2H4 gas, right? Which is the same equation as the equation for which we're trying to find delta H, right? So to find delta H, what do? We simply add this to this to this because we add these 3 equations to get this 4th equation here. So I'm going to do that now. 787.0 plus 1410.9. Oh, I just realized I made a mistake. This here should be negative. All right, so let me do this over again. Minus 787.0 plus 1410.9 minus 571.6. And according to my calculations, this works out to be equal to delta H equals to 52.3 kilojoules. All right. So that's basically how that is done. All right. Any questions about this particular example? Any questions?
I don't think so. Pretty clear.
Mm-hmm. Yeah. I would say that pay attention to little things like the mistake I made earlier. You might leave out a negative sign when it should be there, and so on and so forth. So, okay, so that's basically how that is done. All right, moving along. So let's talk about standard state conditions. Now, the thing about enthalpy changes is that they are dependent on several external factors, including pressure and temperature, right? So in order for us to make meaningful comparisons between reactions based on thermochemical data, what the powers of that be decided on is to adopt what we call standard conditions with respect to enthalpy changes, or for that matter, any thermodynamic data. So the standard conditions are basically what you see here. 1 atmosphere, and it says here temperature of interest, but usually that temperature is 25 degrees Celsius, right? Unless otherwise stated, right? So 25 degrees Celsius would be the standard temperature, and 1 atmosphere would be the standard pressure. Before I move on, let me just say that please do not confuse these standard conditions for STP conditions that we talked about in the chapter on gases. Chapter, was it 5? Right? Those are two different things, right? STP stands for standard temperature and pressure, where the pressure is 1 atmosphere and the temperature is 273 Kelvin. But here, in the case of thermodynamic data, the standard conditions is 1 atmosphere and 25 degrees Celsius, right? So basically, any enthalpy changes that are made under these conditions are said to be standard, right? So we call them standard enthalpies, and we symbolize that using this representation here. We have delta H, but we add to that an O as a superscript to the right of the H, all right? So whenever you see this here, delta H, in reference to any enthalpy measurements, it's referring to the fact that those measurements were made under standard conditions of 1 atmosphere and 25 degrees Celsius, all right? And they're actually, well, before we get to that, and then when it comes to standard enthalpy of formation, right, of a substance, that is the enthalpy change that occurs for the formation of 1 mole of the substance from its elements when both products and reactants are in their standard states, right? So basically what we're saying is that, for example, let me go back to my writing pad here. What is this here? Oh, I need to get rid of this. Okay, let me go to my writing pad here. Let me get rid of this. Okay, so when we're talking about enthalpy of formation, standard, right? Basically, we're assuming that 1 mole of the product or 1 mole of the substance is being formed. So let's say, for example, we're talking about the enthalpy of formation of H2O, all right? So basically, what we're looking at here, okay, what did I do here? What we're talking about here is the formation of 1 mole of water from its elements, right? So the equation for that reaction would be H2 gas plus half O2 gas to give H2O liquid. And you have to be specific in terms of the state symbol. It could be liquid, gas, solid, whatever. So basically, whatever the enthalpy change of this reaction is, as it is written, that would be the enthalpy of formation of water. Here's another example. Suppose you're given C6H6, which is a compound known as benzene, which is a liquid. If you're talking about the enthalpy of formation of benzene under standard conditions, then basically the equation for the reaction for the formation of 1 mole of benzene would be 6C solid plus 3H2 gas, and that would be the equation for the formation of 1 mole of benzene from its elements, all right, under standard conditions. Okay, so I just thought I should make that clear so you understand what that means. All right, so let me, okay, now there are tables that have been put together which gives you the enthalpy of formation under standard conditions of different substances. So what you're looking at here on the screen is basically a small portion of such a table, right, with some important compounds. So for example, in the case of carbon monoxide gas, this is the enthalpy change for the formation of 1 mole of that gas from its elements. Or in the case of, let's say, dinitrogen monoxide, 82.05 is the enthalpy change for the formation of 1 mole of that compound from its elements. Now, there is a more comprehensive table, of course, provided for you in Canvas. Let me show you where it is. Let me go to, okay, so this is your class Canvas shell. If you go to Files, and then go to Tables, and then you go to where it says Thermodynamic Data, and let's download that. So this is a table that you'll have reference to. So whenever you're doing any calculation involving enthalpy changes, then you need to use the data provided in this table. Now, you'll notice that in this table, you have 3 columns. One for enthalpy of formation, the second one is for free energy of formation, and the third one is for entropy. Now, for our purposes in this course, you do not need to be concerned with the latter 2, right? You're going to meet these later on in General Chemistry 2 when you do, when you get to do the topic of thermodynamics, right? So for our purposes, for this chapter, we're only concerned with the data that you'll obtain from the first column right here, all right? So please make a note of this. Another thing I want to point out here is that you'll notice if you examine this table, that when it comes to elements in their standard states, under standard conditions, you'll notice that those elements will have an enthalpy of formation of 0, such as aluminum, arsenic here, and if you scroll down, you see barium, boron, bromine, all these elements, their enthalpy of formation is 0, which makes sense if you think about it, because if you have an element that is naturally occurring under standard conditions, and it's not formed from anything else, then the enthalpy of formation of it would be 0, right? 0 kilojoules per mole. And as you continue here, you see cesium, you see chlorine, which of course exists as a diatomic molecule. So all these elements that exist under standard conditions in their natural form, in their standard states, have an enthalpy of formation of 0. All right. Now, these tables are useful because you can actually use this data to calculate the enthalpy of formation, or I should say the enthalpy of a reaction under standard conditions. And I think I have an example of that coming up shortly. But before we do that, let me just show you how we actually do that calculation. So if you have the table at your disposal, which you do, then basically all you have to do to find the enthalpy change of a reaction is that you sum up all the enthalpy of formation of the products and minus from that the sum of the enthalpy of formation of the reactants. And in each case, what you need to do is multiply each of the enthalpy of formations of the individual substances by their corresponding coefficients in the balanced equation. So this is yet another reason why you have to ensure that you're using a balanced equation to do this work. All right, so it's basically the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants in order for you to calculate the enthalpy change of a reaction under standard conditions, with each coefficient multiplied by, or with each standard enthalpy value multiplied by their respective coefficients. All right. Now, another additional note that is made down here is that when it comes to organic compounds, it's more convenient to use enthalpy of combustion as opposed to enthalpy of formation, right? And the reason why basically is because the enthalpy of combustion data is more readily available, it's more obtainable experimentally. So therefore we use enthalpy of combustion data in pretty much the same way as we use enthalpy of formation when it comes to finding out the enthalpy change of a reaction. So what I'm about to describe in the example that I'm going to provide for you is how we go about determining the enthalpy of a reaction using the data in the table. So you have 2 examples here. The first example gives you this reaction here. And the question is asking for you to find the delta H value for that reaction, all right? So what I'm going to do is, get out of this, I'm going to copy this here and paste it after cleaning up this. Okay, how shall I make this smaller? Okay, I think this is good enough. Okay, so this is the equation given here, right? And the question is asking for you to calculate delta H. So what the first thing I would do here is I would write down an expression based on the equation. And the expression will go like this. Well, remember it's always enthalpy, the sum of the enthalpy of formation of the products minus those of the reactants. So I'm going to start off with the products first, right? Carbon monoxide and hydrogen. So delta H standard for the reaction will be equal to, okay, let me put open parentheses here, 4 times the enthalpy of formation of carbon monoxide plus the enthalpy of formation of hydrogen. All right, so those are the products. Yes, sir.
In the formation of H,
oh,
yeah, I was about to say
thank
that.
you. Thank you. Yeah, okay. Yes, very important point. Multiply each of them by their respective coefficients. Okay, then we do the same thing for the reactants, all right? There are 3 reactants. You have methane, so 3 times enthalpy of formation of CH4 plus 2 times, oh, and by the way, the state symbols are very important. Yes, yes, all right? When it comes to the H2O, 2 times enthalpy of formation of H2O liquid plus the enthalpy of formation of CO2. All right, so that's basic, and this is for the reactants. Okay, so all we have to do now is go to the table and look for the data. So the first one would be for carbon monoxide, 4 times the value for carbon monoxide. So I have a hard copy of the data here, which I'm looking through. And according to this, for carbon monoxide, the value of the enthalpy of formation would be minus 110.53 kilojoules, all right? Plus the enthalpy of formation of H2. But guess what? H2 is an element that exists as H2 under standard conditions. So therefore, I don't even need to look at the table. I know that it will be 0. So A times 0 would be what would go there, right? So that takes care of the product side. And then on the reactant side, 3 times the enthalpy of formation of methane. So let me see if I can find methane CH4. And according to what I have here, CH4 has a value of 52.26. So 3 times 50, no, wait a minute, wrong thing I'm looking at. CH4 minus 74.81 kilojoules, all right? So that takes care of the methane. Then we add to that 2 times the enthalpy of formation of H2O liquid. So if you look at the table, let me see here for H2O, there are 2 values, one for H2O liquid and one for H2O gas. We're going to use the liquid. So 2 times minus 285.8 kilojoules plus for CO2 minus 393.51 kilojoules, right? Okay, so all we have to do now is the math. Well, let me take care of the product side first. So that would be minus 110.53 times 4. So according to my calculation, this part would be equal to minus 4, 4, 2.12 kilojoules. And then that will minus, okay, on the reactant side, let's see here, 3 times 74.81, which is minus negative. And then I add to that 2 times 285.8 negative. And then I add to that minus 393.51. Okay, so the answer I got here is minus 1189.72 kilojoules. And then we simply add those two together. So let me do that here. 442.12. Okay, so the answer I got, and I have to round this off to 2 decimal places, so it's going to be, excuse me, 747.60 kilojoules. And that's basically how that is done. All right. Okay, any questions about this particular example?
The result enthalpy, it's positive, so that means that this is a, let me think
Hold
here,
on.
an endothermic reaction.
Exactly, right. So it's endothermic.
Cool.
Okay. Any other questions about this? Any other questions? Okay, moving along. We're almost at the end of this chapter, actually, but we have one more example and some other things to discuss. So this example right here, let me copy and paste it again. Okay, let me bring this up here. Okay, so in this question, it's pretty much the same idea. The only difference between this is that in the previous question, you're asked to find delta H, right? But in this question, they gave you delta H. And the question is asking for the enthalpy of formation of isopropyl alcohol, which is this compound right here, right? This compound right here is what you need to find the delta H of. So it's the same idea. So the first thing I'm going to do again is write down an expression for the relationship between the different delta H values under standard conditions. So I'm going to say that delta H standard is equal to, starting with the reactants, 2 times delta H formation standard of isopropyl alcohol. Now, I'm too lazy to write out the whole formula for this, so I'm just going to write IP for isopropyl alcohol as an abbreviation, all right? Plus 9 times the enthalpy of formation of O2, all right? So that takes care of what happens on the, actually, I just realized I made another mistake. It should be products minus reactants. So I should have started off with the products first. So let me erase all of this here and restart. So it's a products first, so delta H standard for the reaction is equal to 6 times the enthalpy of formation standard of CO2 plus 8 times the enthalpy of formation standard of H2O liquid, CO2 gas, and then minus, so that those are the products, and then on the reactant side, 2 times the enthalpy of formation standard of isopropyl alcohol plus 8 times, 9 times enthalpy of formation standard of O2, all right? And then for all we have to do from here is put the numbers in, so delta H standard would be equal to 6 times the enthalpy of formation of carbon dioxide, which is minus 393.51 kilojoules, plus 8 times the enthalpy of formation of H2O liquid, which is minus 285.83 kilojoules. All right, so these are the values for the products, and then we minus from that 2 times the enthalpy of formation of isopropyl alcohol, because that's what we're trying to find. And of course, because oxygen exists as O2 under standard conditions, that would be 0. So therefore, this would be 0 here for the oxygen. Now, the delta H value here is given. This is given in the question here. So that is equal to minus 4011 kilojoules. So basically, all we have to do now is do the arithmetic. Minus 4011 kilojoules. I'm going to work out what's within the parentheses here. So 6 times 393.5 minus, and then we add that to 285.83 times 8. Okay, so according to my calculations, this part here works out to be equal to minus 4647.64 kilojoules. And we're going to subtract from that 2 times delta H formation standard of isopropyl alcohol. Okay, so basically what we're going to do now is add 4647.64 to both sides. So this will give you 0. So basically, let me do this here. So 4647.64 minus 4011. And the answer I got here is 636.64. So you're going to end up with 636.64 kilojoules, 64 kilojoules equals to 2 times the enthalpy of formation of isopropyl alcohol. So therefore, enthalpy change formation of isopropyl alcohol is equal to 636.64 kilojoules divided by 2. So when I divide by 2, the answer I end up with is 318.32 kilojoules. And that would be the answer for this question. So it's the same principle, just a matter of, you know, a different value that the question is asking for, which in this case is the enthalpy of formation of one of the substances involved, and it gives you the enthalpy of formation or the enthalpy of the reaction overall. All right. Okay. Any questions about this one?
It's the enthalpy of combustion is a lot different from the enthalpy of formation. It seems like you're getting a lot more energy out of it than you put into it.
In the case of combustions, especially when it comes to organic compounds, hydrocarbons and so on, they usually have very large values in terms of how exothermic the reaction is. And that's why, for example, a lot of organic hydrocarbons are used in fuels, such as gasoline. Gasoline is a mixture of hydrocarbons. When ignited, gives off energy in the form of heat and light and so on.
Yeah.
When it comes to enthalpy of formation, it depends on the stability of the compound in large part. There are other factors as well. In fact, again, for those of you who plan to do Chem 2 in thermodynamics, you're going to learn about why is it that some reactions will take place and others will not. And part of it has to do with enthalpy. So the other part has to do with entropy, which you won't meet until next semester or whenever you do Chem 2.
Right.
So it's not a guarantee that all organic compounds or compounds in general will have a negative enthalpy of formation. And of course, you definitely won't assume that all reactions will have a negative value. There are some reactions that will, and there are some reactions that will have a positive value, right? Some reactions are just simply endothermic under normal conditions or standard conditions, and other reactions are exothermic. And one predictive tool is delta H, but that is not the sole predictor of whether or not a reaction will be occurring. And I don't want to say anything more because that will delve into what you guys will get into in general chemistry too, right? There's a whole chapter where you'll have the opportunity to learn and discuss and understand that. Okay, let's see what next. Oh, you can also have standard enthalpy of formation of ions in aqueous solutions, and this is a table. I don't think the table, yes, this table do have some of those data. So you can have calculations involving ions as well, all right? And this is just basically some general information I alluded to earlier about fuels. Basically, fossil fuels are formed, of course, over millions of years because organic matter become buried and compressed under mud and water, right? So all the fuel that we have been using in our gasoline and so on actually comes from these sources, all right? And basically when they're burnt, as I said before, when they're combusted, they release a lot of heat and energy. And basically that's, you know, how fuels work in terms of providing energy and heat. And fuels for the body, which would be foods, also provide energy. And there are three principal classes of foods that are fats, proteins, and carbohydrates that provide energy for our bodies, all right? And that's basically all, that's basically it for this chapter, all right? So if there are no questions concerning this chapter or anything else in relation to this chapter, we're going to move on to chapter 7, all right? And in chapter 7, we'll be dealing with the atomic structure, all right? I think I alluded to some aspects of the atomic structure before, but now we're going to get into it in more detail, all right? So the current modern view of the atomic structure, we arrived at it starting with the classical view. Now the classical view, just to give you a brief description, way back when, I don't remember exactly the dates. I'm not good at remembering dates of events, which is the reason why I'm not a history major. But back then, it was thought that small particles like electrons behave pretty much in the same way as larger particles that we are accustomed to, right? So, you know, people used to believe that electrons behave the same way like balls or whatever, and therefore the way they move and the way they bounce into each other and all of that would be pretty much the same way as, you know, common objects that we're accustomed to. Then some people did some experiments with light, which basically contradicts that classical view, which brings to light what is now known as the quantum theory, which is used to basically explain the behavior of small particles like electrons, atoms, and so on. So as a result of the quantum theory, we now have the quantum view, which describes the behavior of electrons in atoms. And that's what we'll be talking about in this chapter. So first thing I want to talk about as we move along in this chapter is how electrons were discovered. Now, electrons were discovered in the form of what we call cathode rays. Now, somebody, I don't remember who it was, came up with this experimental design. Let me try to describe what's happening here. So you have a tube here, which is evacuated, right? So there's no air inside this tube. At both ends of the tube, you have two electrodes. electrodes are basically metal plates which are connected to an electricity source, right? So this plate here, which is connected to the negative end of this electricity source, is called the cathode, and this here is called the anode, all right? The anode is positively charged, the cathode is negatively charged. So when this connection is made, what was noticed was that there was a stream of particles emitted from the cathode and moving towards the anode, all right? And these particles have certain properties. For one, obviously, these particles will be negatively charged because they're leaving something which is negatively charged, which is a cathode, and being attracted to the electrode, which is positively charged. They also travel in straight lines, and they also can be deflected by a magnetic field or an electric field. So in this picture here, which is basically a recreation of the same experimental setup, here we have the cathode rays, and you have the magnet down here, and you see that the cathode rays are deflected towards the magnet, all right? Another property of cathode rays is that when they hit materials such as glass, they fluoresce. In other words, basically they shine or brighten up, all right? So those are just some properties that were initially observed about these cathode rays when they were first discovered. So J.J. Thomson, a physicist, he examined these rays in more detail, and he came up with a modification to the original setup, which looks like what you see here on the screen. So you have your cathode and you have your anode, but instead of a solid anode, you have a slit inside the anode, right? Which allows the beam, which is energetic enough to pass through it. And there's another slit just to make sure that you have a beam emerging from this region. And then the beam is allowed to go into this region right here. Now, in this region, you have two magnetic poles, and you have two electrical condenser plates. And what is done here is that the electric field and the magnetic fields are adjusted so that you can have the deflection of the beam. So as you can see here, the beam can be deflected up, or if there's no field here, then the beam will just pass right through, or it can deflect down, right? And you have a scale here which measures the angle of deflection, all right? So based on this setup and some mathematical work that was done, which I won't go into, J.J. Thomson discovered something about these particles. He discovered that the mass to charge ratio of these particles is equal to minus 5.686 times 10 to the minus 12 kilograms per coulomb. Coulomb is a unit of charge, all right? If I don't know how many of you have done physics or plan to do physics, but I'm willing to bet that when you get to your physics course and when you guys start talking about, I think it's where you're talking about electricity and magnetism, you will actually do the calculations to see that this number is derived, all right? Okay, so that was one major development that was made in the steps for discovering the actual nature of these particles, right? So this is what J.J. Thomson discovered, the mass to charge ratio of the particles, which were subsequently called electrons, is equal to minus 5.686 times 10 to the minus 12 kilograms per coulomb, all right? So this guy here is the person who actually coined the term electron. So therefore, of course, scientists were not satisfied with just knowing what the mass to charge ratio is. They want to know what the actual mass and what the actual charge of the electron is. And that was discovered by this guy, I think he was from Holland, Millikan, right? His famous oil drop experiment. And just to describe what's happening here, here we have two plates, which are electrodes, which are connected to an external circuit. You have some oil here in a bottle with a nozzle that can spray it into fine droplets. Now, this particular electrode here, which is the anode, has a very tiny hole, so oil droplets will come through here and end up inside this region right here. And you have some radiation here, which will ionize the molecules of the oil droplet. Now, because this has a charge, you can actually adjust the electric field between the two plates so that the oil droplet is suspended between the two plates. And based on that suspension and other data and so on, Millikan was able to calculate the charge on the electron. So he determined that the charge on the electron is equal to minus 1.602 times 10 to the minus 19 coulombs. So based on J.J. Thomson's experimental result, where he determined the mass to charge ratio, and based on Millikan's determination of the electronic charge, then all you have to do is multiply the electronic charge by the mass to charge ratio, and that will give you the mass of the electron, which is equal to 9.109 times 10 to the minus 31 kilograms. All right, so again, another important step for scientists on the journey of determining the nature of a subatomic particle such as the electron. Okay, so this now begs the question, okay, now that we know that we have electrons present in atoms, how are they arranged, right? How are they put together in the atom along with the other particles, protons and neutrons, right? So, you know, people came up with different models. J.J. Thomson's model was what we call in some textbook, the plum pudding model. And basically what he proposed is that an atom with a positively charged sphere containing equally spaced electrons inside is basically how the electrons are arranged in an atom, right? So according to, well, let me just say this. Before I move on to the actual model, there's one thing I neglected to mention. Upon discovery of the electron and knowing that the electron is negatively charged and knowing that the atom is neutral, then of course the logical conclusion that there's some other part of the atom that is positively charged, right? So what J.J. Thomson was suggesting is that the model of the atom would be where you have the electrons embedded in a large positive nucleus, all right? So the picture of the atom would look something like this for helium, for example, according to the model put forward by J.J. Thomson. You have a large nucleus, and then embedded in the nucleus are the electrons that are equally spaced, all right? So that was a model that J.J. Thomson came up with, all right? Now, of course, people will try to test that model to see if there's any truth to it. And another guy, Rutherford, came up with an experiment which tested it and found it not to be true. So this is the diagram showing you the experiment that Rutherford came up with. Consists of a metal foil. If I remember correctly, that foil is made of gold. And then he had a source of alpha particles. Now, alpha particles are basically the nuclei of helium atoms, all right? In fact, specifically of the helium-4 isotope, all right? Now, these particles are positively charged. Now, if J.J. Thomson's model was true, one would expect that these positively charged particles, when they are shot from here and hit the metal foil, they will simply bounce back because they will simply hit the nucleus, which is, according to the model, the bulk of the size of the atom, and therefore, because of repulsive forces between the nuclei and the alpha particles, they will simply bounce back. What Rutherford found out was that, in fact, most of the particles will pass right through the metal foil and can be detected on the other side, all right? Now, most of them will pass through in a straight line fashion. Some of them will pass through and be deflected, like here and here, and the others will be turned back as shown here, all right? So basically what this shows us is that the Rutherford model, I'm sorry, not the Rutherford model, but the J.J. Thomson model is not true. In fact, what is more likely to be true is that the atom, in terms of its size, is basically occupied mostly by electrons, and in terms of the mass, it's more concentrated in the middle. And that makes sense in light of the experimental result of Rutherford, because if that's true, then it makes sense that most of the alpha particles will pass right through the atom without encountering any particles. If it does encounter the nucleus, it may encounter the nucleus and be deflected as shown by pathway 3 right here, or according to pathway 4 here, where it is turned around, all right? So that's basically the Rutherford experiment. And as a result of the Rutherford experiment, we now know that the structure of the atom is where you have a positively charged nucleus, which is very small and dense, while most of the volume around the nucleus is occupied by electrons, which are more spread out and diffuse, all right? Okay, so that's the Rutherford experiment and the Rutherford model. All right, now, of course, based on Rutherford experiment, he was able to determine the amount of positive nuclear charge, and the name given by given to these particles are they're now called protons, all right, which are residing in the nucleus. And this introduced the concept of the atomic number. The atomic number, which of course we all know by definition, is the number of protons that are present in the nucleus of an atom, all right? And then much later, if I remember correctly, about 3 decades later, an Englishman by the name of James Chadwick, he discovered the neutrons in the nucleus. So the discovery of the neutrons kind of was eluded because the technology at the time did not allow for the detection of anything that is neutral, right? It was easy to determine, relatively speaking, the electrons and also the protons. But James Chadwick, it took some time for James Chadwick to determine that there's also neutrons present. But there was some hint that the neutrons or some other particles were there, because some people discovered that, okay, if we know the number of neutrons, I'm sorry, if we know the number of protons and we know their mass, when they compared that to the size or the mass of the atoms, there's a difference. So there was some suspicion about some other particle, but it eluded discovery until James Chadwick designed an experiment specifically for the discovery of the neutrons. So now we know, in our current understanding of the structure of the atom, that there are 3 particles: protons, neutrons, and electrons. Okay, let's talk about mass spectrometry. This is a device that basically separates gaseous ions according to their mass to charge ratios. And the record of the separation of these ions is called a mass spectrum. So what you see here is an example of mass spectrum. If I'm not mistaken, this is for mercury, all right? So what they did here, or what the device does, is separate the ions according to their mass to charge ratios. And because mercury has several isotopes, you have different peaks, right? So the most abundant isotope is the one with the mass of 202 AMU, but you have some others as well which are less abundant. Now this is how it works. So you have the stream of positive ions that are created, and they are ushered into this region here, which has, in this region here, a magnetic field. So when the magnetic field applies, the effect that it has on the positively charged ions is that it causes them to move in a circular fashion. Turns out that the heavier particles will take a pathway with a larger radius, while the smaller particles will take a pathway with a smaller radius, right? So that's a basis for the separation of these ions. And then they're allowed to hit the photographic plates, and that produces the mass spectrum for the mercury vapor, right? So as you can see here, the most abundant ion is the one that hits here, which has the mass of 202 AMU, all right? And mass spectrometry is a very important technique for determination of structures, especially when it comes to organic molecules. So for those of you who have to do organic chemistry, you're definitely going to need this technique later on. Usually it's introduced in organic too. Okay, I think I'm going to stop here because this deals with a topic which I don't want to stop in the middle of. So I'm going to call it today. So let's stop here, and give me a minute. Let me get my grade book so I can take roll. Hold on 1 minute. Okay, let me see. Okay, let me stop sharing here. All right, let's see who is here. Today is the 24th. Okay. Arias Rios. Barber.
Here.
Cannon is here. Chang is not here. Chavis, not here. Clark, not here.
Here.
Oh, Clark is here. Sorry, my bad. DeGraff, Franklin, Han, Panic, Tyron, Holland is here. Jurgensen, not here. Rees, not here. Rouse is here. Ronalds is here. Santiago is here. Smith is not here. Okay. All right. So that's basically it for today, unless there are any questions about this or anything in general. Any questions? No?
No, I don't think so.
Okay. All right. Well, that's it for today. I think I'll be posting a quiz tomorrow, so look out for that. And then that's it. All right. So have a good weekend and take care.
All right. Take care.